Okay. Hello, everyone. So my name is Chen from Duke University. So this work I will present the differential private stream processing. So this work is collaborated with my advisor Ashwin and Professor Hay from Colgate University and Professor Miklau from UMass. So in today's world, a lot of applications domain rely on the personal data, which is processed in a streaming manner. So the streaming data has become the foundation of the IoT stuff and is very prevalent in domains of many applications like environment sensing, traffic management, health monitoring. So because the streaming data is usually captured and analyzed continuously, and we know it has large volume, we should process as it arrives in real time. So however, a lot of data contains the private information of the individuals whose data are being connected. So for example, the environment sensing or the traffic management applications may use your location information. Also, the health monitoring applications may get the health status information of the individuals. So these data are sensitive. So directly release this data or even some aggregates of data will leak the privacy of individuals, which the users do not want. So therefore, we need some way to do the stream processing under certain strong privacy guarantees. And in this work, we'll apply the differential privacy. So differential privacy was proposed about 10 years ago and it became the gold standard privacy definition due to its approval guarantee and good composition properties. So differential privacy defines labeling data set as they differ by addition or removal of a single record. Then differential privacy guarantees that for every pair of labeling data set and every possible output, the adversaries who see the output will unable to tell which one is the input data set. So from the math side, it tells that any randomized algorithm A satisfies absolute differential privacy if the log ratio of the probability that the algorithm gives the same output for any two labeling data set, D1 or D2, is bounded by epsilon. Here, the epsilon, we call it privacy budget, which controls the privacy level. The smaller epsilon implies stronger privacy guarantees. So differential privacy has the following very beautiful composition properties. So suppose A1, A2 be the epsilon 1 or epsilon 2 differential private algorithms. Then the sequential composition means that if we compute A1, A2 on the same data set, it will guarantee the epsilon 1 plus epsilon 2 differential privacy. The parallel comparison means that if we compute the same algorithm A1 on two disjoint datasets, it will still ensure the epsilon 1 differential privacy. And the post-processing means that any post-processing in terms of output for any differential private algorithms will not incur actual loss of privacy. So which means that the post-processing operations are safe in terms of privacy. So these three composition properties help the researchers to design much more complex differential private algorithms by just composing simple ones. So in this work, we define the stream data model as follows. So we define the source stream data as an infinite sequence of tuples. So one tuple UST will mean that the user U was observed in state S at time t. To make it simple, we use logical timestamps. So every timestamp will represent one time interval. So a tuple UST will be the aggregate behavior of the user U associated with state S at time t. So in this work, we only focus on the counting queries as well as all the other queries which can be derived from the counting queries. So for each state, we can derive a count stream, the CS, and the count CTS reports the number of users associated with state S during the T time interval. So here is an example. So suppose a lot of Wi-Fi sensors are distributed in the building. Then we mean each sensor will represent one state. So if a user U connected to the one Wi-Fi sensor S at time t, so we will generate one tuple, UST. So in order to use a logical timestamp, suppose here we set the time interval to be every 5 minutes. So the UST will mean that the user U connected to the Wi-Fi sensor S during the T time interval. So we can derive the strings for each sensor S, which will report the number of users connected to the sensor during every 5 minutes. So there are many interesting queries in terms of the stream. First, we may want to ask how many users connect to each Wi-Fi sensor during every 5 minutes. Or also we want to ask some aggregate information, like how many times the users connected to the Wi-Fi sensors during the most recent 1 hour. Also, we want to detect interesting patterns in terms of stream. Like we want to know whether there are certain big changes in counts during the recent time, or where there's some consistent low counts during the recent time. So in this talk, I will only focus on the queries in terms of a single target state. So all the extensions in terms of multiple target state have been discussed in our paper. So if you are interested, you can read the paper. So the online query answering for data stream under differential privacy is not a new research. So a lot of previous works, but there are two drawbacks of the previous techniques. Firstly, all the previous techniques are designed for any specific workload, which means that if we want to ask multiple queries, we may use different algorithms, which means we want to split our price budget. Also, all the previous techniques are data independent. So these algorithms are designed for the worst case data distribution. So in this work, we propose a new algorithm called Pegasus, which addresses the two drawbacks above. Firstly, our Pegasus will simultaneously support multiple queries from the single output without splitting the privacy budget. Also, our Pegasus is data dependent, which means the injected noise will be adjusted according to the input data distribution. So this is the outlines of my following talks. I will first show you our chosen privacy model. Then I'll introduce you our proposed new Pegasus algorithms for doing the stream processing. So finally, I will end my talk by showing you some evaluation results. So for privacy model. So we want to apply differential privacy in the work. And we have just discussed that differential privacy protects the presence or absence of a deferred record in any labeling data set. So here in this work, we apply event-level differential privacy. So in the 11 differential privacy, the labeling data set are defined to differ by one single tuple. So in the Wi-Fi sensor example, it will protect the adversaries from knowing whether any single user connected to Wi-Fi sensor during the one-time intervals. Although it looks a little bit weaker, but the event-level differential privacy will automatically capture some stronger privacy guarantees. For example, the W-event differential privacy. So the W-event differential privacy defines the labeling data, which is to differ by the tuples associated with one user within W timestamps. So in the Wi-Fi example, it will protect the adversaries from knowing whether any single user connects to the Wi-Fi sensors during W time intervals. So we can see that any algorithms that satisfy ipso event-level differential privacy will also ensure the W times ipso W event differential privacy by just using sequential composition properties. For more stronger privacy definition, like the user-level differential privacy, which define the labeling data to be differed by all the tuples associated with one single user. So here in the Wi-Fi example, it will protect the adversary from knowing whether any single user connects to the Wi-Fi sensors at any time. We can also say that any algorithms that satisfies ipso event-level differential privacy will also ensure the L times ipso user-level differential privacy, where the L here is bounded by the length of the stream. So in this work, we'll only focus on designing the algorithms which satisfy event-level differential privacy while minimizing error. So now next, let me show you our Pegasus algorithm. So this is an overview of the algorithm. It contains 3 components. There's one perturber, one grouper, and one smoother. So the perturber of Pegasus consumes the input data stream and add noise, perturb each incoming element, and output a stream of noisy count. The grouper is trying to group, it also consumes the input stream, and it tries to group the elements seen so far, which share similar counts. And the smoother is only a query-based post-processing step, using output from the perturber and the grouper. So here you can see that only the perturber and the grouper will access to the real data, so in which we should introduce noise to make it private. The smoother is just post-processing, which is safe in terms of privacy, and it can be anything. So let me show you how each of the components can be implemented. So for the perturber, it does a very simple thing. It's trying to perturb each incoming element. So here we directly apply the most basic Laplace mechanism. So the Laplace mechanism perturbs the output of any function by adding a Laplace noise with a parameter equal to delta f over epsilon. The delta f is called the global sensitivity of function, which is defined to be the maximum L1 distance between the function and any two labeling data sets. And the Laplace mechanics has been proved to satisfy differential privacy. So for the grouper tries to group the elements seen so far which share similar counts. So given the following streams, so I just show you a very good grouping result. So here there are 3 groups, and each group will contain the elements share similar counts. So for the grouper, we propose a deviation-based online grouping method. Now here is the intuition for the grouper. So when a new element comes at the current time, we first check whether we can add the current element into the previous group by considering the deviation values when we combine them together. So usually the smaller deviation values of a group implies more uniform in terms of elements of the group. So if a deviation value is small, we will directly add the current element into the previous group and done. If the deviation is big, we first seal the previous group and the current element, and we will start a new process at the next timestamp. So let me show you a very simple example of the grouper. To make it more simple, we suppose epsilon go to infinity, so there will be no noise introduced. And there is another threshold parameter theta, which helps us to determine whether the deviation is big or not. So here we give a string of 5 elements. So at the first time, we will start a new process with a single group which contains the current index. So at second time, now a new element comes. We first compute the deviation values when we're trying to add the current element into the previous group. I will find that the deviation value is smaller than the threshold theta. So we directly add the current index into the previous group. At third time, a new element comes. We first compute the deviation value when we combine the new group, and it's still smaller than the threshold theta, and we directly add the current element index into the previous group. But at time 4, when we compute the new deviation values, it becomes greater than the threshold. Now what we do is that we first seal the previous group, and then we seal the current element as a single group. So at the next time, at time 5, we'll start a new process with the single group containing the current index 5. So to make the grouper private, we will add noise to both the deviation values and the threshold theta. Actually, a lot of experts will find that each process is actually an application of a sparse vector technique. And the sparse vector technique has been proved to satisfy differential privacy. Also, in terms of different process, its computation is based on the disjoint data. So we can analyze the privacy protection by using the parallel composition of differential privacy. So for the smoother, so what the smoother does is that it computes answers to the queries based on the output from the perturber and the grouper. So we have discussed that the smoother is only the post-processing step, so which is safe in terms of privacy. So we can do anything we want, so we can design different smoothers for different queries. So let me show you an example. Suppose we want to design a smoother for answering unit counting queries. So the unit counting queries ask for the single count at every time step. Here, given the real time, give a real string, and we have one output noise stream from the perturber. Also, we have a grouping result from the grouper, and we want to ask the single count query, suppose at time t. Then one estimate is that we can directly use the noisy count from the perturber. But we can do better. We know that the elements in each group from the grouper share the similar counts. And we know that the last group GI will contain the current index T. So we can use the median of the noisy count indexed by the last group GI to be the better estimate of the current element. Also, if you want to design a smoother for W sliding window queries. So a W sliding window queries ask for the total count sum during the recent W timestamps. Here again, given the real stream, we have a noise stream from the perturber. We have a grouping result from a grouper. Then suppose the window size is 5. We can get one estimate directly from the perturber by summing up the most recent five noise count. But we can also get a better result from the group by using the grouping result. Here we know that the GI-1 and the GI contain the target window. Then for each element in GI-1, we can use the median of the noise count indexed by the group to be the new estimate for each of the elements in the group. The similar things for GI, we can use the noise median of the median of the noise count indexed by the group GI as a new estimate for each element in GI. So the new estimate for the sliding window queries can be summed up with this new estimate counts. So now let me show you some evaluation results by using our Pegasus. So the data set comes from the real traces taking over a 6-month period and from approximate 4,000 Wi-Fi sensors distributed across the campus of a large educational institution. We use logical time, so we set the time interval to be 5 minutes. So for each sensors, we can derive a count string, which report how many users connected to the Wi-Fi sensor during every 5 minutes. So we pick 3 representative sensors with a different load, and we have 3 streams here. So this table shows the overview of the streams in terms of the name, the length, the total counts. So the first few figures show the visualization of streams in terms of the stream high 5 for the first 8,000 timestamps. The left 2 figures report the real stream, and the middle 2 is the output from the previous Laplace mechanism. And the right 2 is from our Pegasus. Apparently, by just real size, you can say that for both ipso settings, ipso equal to 0.1, ipso to 0.01, our algorithm leads to much better streams. We also evaluate the answering unit counting queries by using the scale total L1 errors. So for each of the 2 figures, the y-axis reports the nocturne value of the scale total L1 error, and the blue column represents the Laplace mechanism. The orange column is our Pegasus. Again, you can see that for both ipso settings and for all 3 streams, our Pegasus has less error for answering unit counting queries. We also evaluate for answering sliding window queries. So for each figure, the y-axis reports the average L1 error, and the x-axis represents the window size in terms of 2 to the power of x. So we compare 4 different algorithms. So yellow lines represent Laplace mechanism, which means that we use Laplace mechanism to perturb the stream first, and then answer the sliding window queries on top of the noise stream. The blue line is a previous state-of-art W window sum algorithm. So W window sum algorithm is designed for answering sliding window queries in terms of any specific window size W. So for each point of the blue line, it represents a slightly different algorithm. So the green line and the orange line are our Pegasus-based algorithm. The only difference is that the orange line will use a smoother, which is designed for the unit counting queries. But in the green line, we use a smoother, which is designed for the sliding window queries. So here you can see that for all different settings, the Laplace mechanism works the worst for all the window sizes. And when the window size is not too big, it's smaller than 2 to the power of 8, our Pegasus algorithms outperforms the previous state-of-art W window sum algorithms. So compare between our 2 Pegasus algorithms, the one which uses a smoother that is designed specific for the sliding window queries consistently better than the other one. But I have to emphasize one more thing, is that even when the window size goes too big, the previous W window sum algorithms outperforms our Pegasus. However, as I just mentioned, the W window sum algorithm is designed for the sliding window queries in terms of any specific window size, which means that if we want to ask sliding window queries with different window sizes, by using the W window sum algorithms, we have to split our privacy budget. But our Pegasus algorithm support all the sliding window queries with different sizes from the single output. We also evaluate our result by in terms of event monitoring queries. So the answers to the event monitoring queries can be represented as a sequence of 0, 1 bits. So the bit bt equal to 1 means that the event happens at time t. And the bit bt equal to 0 means that the event does not happen at time t. So we consider two interesting patterns in our work. One is to detect the jumping and dropping points. So a jumping and a dropping point happened at time t if the difference between the count at time t and the count W times before is greater than the threshold delta. Another interesting same event is to detect no signal point. A no signal point happened at time t if the W window sum query answers at time t is smaller than the threshold delta. So we use also curves to evaluate this answering the event monitoring queries. So for each algorithms, we change the threshold delta values in the algorithm. Then we compute two values. One is the true positive rate value, which is defined to be the number of times the happened event correctly to be detected over the number of times the event actually happened. And the false rate value, which is defined to be the number of events that the event are falsely detected to happen over the number of times the event does not happen. So the also curve is now defined as the TPR values versus FPR values over all possible threshold data. So there's another measure AUC, which is called area under the curve, which help us to determine how good the performance of the algorithm. Usually the larger AUC is implies a better performance. So here we compare the Pegasus algorithm with the Laplace mechanism on detecting the jumping and dropping points. You can see that our Pegasus has larger AUC values showing its better performance. A similar results for other settings. Also, we compare our Pegasus algorithm with the W window sum algorithm on detecting the no signal points. Still a similar result. We have the AUCs from our Pegasus algorithms is larger than the W window sum algorithms, which show its better performance. So here is a brief summary. So we present a new data-dependent differentially private algorithm, Pegasus, that can simultaneously support a variety of queries from just one single output without splitting the privacy budget. Also, our Pegasus simultaneously support a range of query workload over multiple resolutions of the streams. And from a comprehensive evaluation, we show that our Pegasus outperforms the previous state-of-the-art algorithms, which are specialized to any given workload. So that's it. Thanks for listening.
Hi, this is Vince from Alibaba, and Sivan you have two modules, and the perturber and the grouper, both working on an epsilon differential privacy, right? And so the total algorithm should have an epsilon of 2 epsilon, right?
Actually, we split the total privacy budget into epsilon 1 and epsilon 2. And in the experiment, we spent like the 30% of privacy budget into the grouper and the 70 left percent of privacy budget into the perturber.
Oh, that's exactly what I want to know. Thank you.
Questions? So it seems like your system has a bunch of different parameters, right? And it seems like for different kind of data, you may want to tune the parameters in a different way, right? Is this true or?
Yes, actually, there are like two main parameters here. One is to like how to split the privacy budget for the perturb and the grouper. Another one is like for the grouper, there's like parameter theta to determine the deviation, whether when the deviation is big and small. I agree with you. Like it's like a empirical result, and actually, this is an open question about like automatically choose the privacy parameters in the differential private algorithms.
Mhm.
It's an interesting question.
And then in your application, so you've only done this for your Wi-Fi application, right? Not other
Yeah. Here's for all experiments based on this real data set.
Wi-Fi. Okay. So in your model, the perturber and grouper, they're all the Wi-Fi access points. Who are those parties? Who's running the grouper? Is it the Wi-Fi?
The grouper, there's like a one sensor, the centralized sensor to run the grouper.
So they all collect. Everything is collected by that central thing, and all the math is done by that.
Actually, we can even do it locally. It's fine because this grouper only take the counts. We can run different groupers for each local part. Still works.
Right. Question.
Hi, Tianhao Wang from Purdue University. So have you tried the exponential mechanism for the grouper? Exponential mechanism. I mean, to define the quality function for each group, and then
No, not yet. How to do the expansion mechanism?
I mean, to allocate the current event to different groups based on the quality function, which is defined by, I guess, the deviation.
I think the main challenge is that even the grouper is an online process. Like every time you have spent the privacy budget on the previous data, you cannot use that again. So here is why we use the sparse vector techniques to group the elements with some consecutive windows. I don't know how to use the exponential mechanism on that.
All right. Let's thank Jan one more time.